Okay, folks, so let's get into this thing and start talking about the common ion effect. And to do that, we're still going to talk about CO2, but a completely different example. Okay? And so I want to talk about biologically how our blood is tightly regulated between a pH of 7.35 and 7.45. So we call this buffered. Or another way we could think of this is it's regulated. So our biochemistry helps regulate the pH of our blood, and it does it via the following: lungs remove CO2 via exhalation, and kidneys remove bicarbonate through some rather complex chemistry that we're not going to get into beyond the scope of this course. Okay, but the way that the body does this, we can imagine this in the following couple examples. So let's say I take a big exhale. So I'm pushing all that CO2 out of my body. So now I've decreased the amount of dissolved CO2 in my blood, right? So keep that in mind. That's aqueous CO2 in my blood. Okay. That's still going to go through this carbonic acid cycle, just like it is in the ocean, but rather this is occurring in our blood. So when I exhale and deplete CO2, or at least, get rid of a lot of it, if we think about the Le Chartier's principle situation here, that is going to make the carbonic acid want to shift back to reactants. And if the carbonic acid then decreases, then that's also going to make the H plus want to shift back that way. So in other words, when we exhale, we're actually influencing our blood to become more basic through this Le Chartier's principle, shifting that equilibrium back to the left. Okay. Well, so now once we've depleted that CO2 and we've diminished carbonic acid, our body wants to respond by shifting the equilibrium again. And it does that by actually consuming bicarbonate. You can see here kidneys remove bicarbonate. And so when the kidneys remove all of that bicarbonate, now the equilibrium has to shift back to the right. So that makes it more acidic. Okay. So there's this constant back and forth between depleting CO2 and depleting bicarbonate. And that's what keeps the pH of our blood tightly regulated or buffered between this very tight, precise pH range. And all kinds of stuff goes wrong with us if our blood is not in that tight range. Okay, so now let's describe this a little bit more. So a buffered solution. So there's a couple ways that we can think of this. So the exact definition is a buffered solution is a solution that resists a change in pH. So in other words, just like that example with blood, where we can either deplete CO2 or we can deplete bicarbonate, we're keeping our pH regulated by allowing it to resist a change. Okay. And so how do we make a buffered solution? Well, quite simply, a buffered solution contains a weak acid, and I'm going to write CB, it's conjugate base, and that would be an acid buffer. Okay, so we'll highlight this. Or, of course, we can have a base buffer, right? And so that means it would contain a weak base and its conjugate acid. So that would make a base buffer. Okay. So once again, a buffered solution, a solution that resists the change in pH. Okay. And a buffered solution is one that contains a weak acid and its conjugate base, or a weak base and its conjugate acid. And it must contain both of these things in appreciable amounts. And for something to be a really effective buffer, we typically want the weak acid, I'll put that in brackets so we know that that's concentration. We want that to be roughly equal to its conjugate base concentration and vice versa. They don't have to be identical, but we want them to be on the same par for the buffering trick to work.